For today's video, we'll be practicing how to calculate formal charges of atoms. For a quick refresher, check out the previous video titled How to Calculate Formal Charges of Atoms Theory, because we'll be using the concepts explained in that video. For the following examples, we'll only be calculating the formal charges of the non-hydrogen atoms only, since all the hydrogen atoms will have no formal charge. So first we want to remember our formula for formal charge. So the formula for formal charge is equal to the total number of valence electrons in a free atom. So total number of valence electrons in a free atom, which is the same as the group number of that atom minus the total number of non-bonding electrons. So the total number of non-bonding electrons minus 1/2 of the total number of bonding electrons minus 1/2 of the total number of bonding electrons. All right, so this is going to be our formula for calculating the formal charge. And to help us visualize these molecules, we're going to be drawing the Lewis structure for each of these molecules. So our first molecule that we're going to be working on is aluminium, which is AlH4 minus. So this is a formula for aluminium. So let's draw the Lewis structure for aluminium. So first we want to count the valence electrons in the ion. So there are 3 valence electrons in aluminum and 1 for each hydrogen, for a total of 3 plus 4, which is 7. However, aluminium is an anion, meaning that it has a negative charge. So therefore we have to add 1 more electron to our total, giving us a total of 8 valence electrons. Because 7 plus 1 equals 8. So next we want to connect any atoms that form more than 1 bond. Right, so now we're going to be drawing our structure. So since there's only 1 multiple bond forming atom, which is aluminum, we will just draw our aluminum atom, because all the hydrogen atoms only form 1 bond, but aluminum can form up to 3. So next we want to connect the hydrogens to aluminum. So aluminum forms 3 bonds, so we can connect 3 hydrogen atoms to aluminum. So let's go ahead and draw our Lewis dot structure. So this is the Lewis dot structure of aluminum. And so we want to connect a hydrogen atom to each free electron on aluminum. So this is going to be our structure so far. So now that we connected 3 hydrogen atoms to aluminum, we want to move on to the next step. For the next step, there's still 1 more hydrogen we need to connect, but we have nowhere to put it. We need 2 electrons to form a covalent bond, but we only have 1 left. But if you remember, we added 1 more electron to the valence electron total. So we'll be using that extra electron to form the last covalent bond. Right, so let's go ahead and draw our last covalent bond up here. So this is going to be the final structure of aluminide. And now we want to do one more thing. We want to add brackets around the structure and then add a negative sign up here at the top right. And these brackets and negative sign indicate that the overall charge of the molecule is negative. Remember, the sum of the formal charges of the atoms in the molecule has to equal the charge of the ion. So if we were to add up all the formal charges in aluminide, it should add up to -1. So let's calculate the formal charge of the aluminum atom, because we're not worried or concerned with the formal charges of the hydrogen atoms. So the total number of valence electrons in a free aluminum atom, or in other words, its group number, is going to be 3. Right, so let's put a 3 right here, right, because we're concerned with the total number of valence electrons in aluminum. And since all the electrons surrounding the aluminum atom is involved in a bond, there are no non-bonding electrons for aluminum. So since aluminum participates in 4 bonds, and since there are 2 electrons per bond, we will have a total of 8 bonding electrons. So we have total number of non-bonding electrons, which is 0, minus 1/2 the total number of bonding electrons, which is 4. So actually make that 8, because there are 8 electrons participating in bonds, right? So 1/2 of 8. So now let's go ahead and do the math. So we have 3 minus 0 minus 1/2 of 8, which is just 4. And so 3 minus 0 minus 4 is the same as 3 minus 4, which is -1. So the formal charge of the aluminum atom in aluminide is -1, which we will indicate with a negative sign next to the aluminum. Right, so let's go ahead and add that negative sign up here. Right, this indicates that the aluminum atom has a formal charge of -1. So notice how the sum of the formal charges are equal to the charge on the entire aluminide ion, since the formal charges on all the hydrogens are 0. Right, so we have 0 plus 0 plus 0 plus 0 for each hydrogen atom, and then plus -1 for the aluminum, giving us a total of a negative overall charge. So that's going to do it for our first example. For our next example, we have hydronium. Right, and hydronium has the formula H3O plus. Right, and so hydronium is a positively charged ion that results from the polarity of water molecules. Because water is polar, its negatively charged region attracts a hydrogen atom from a neighboring water molecule, and that's what gives us the formula H3O plus. So now let's calculate the formal charge on oxygen, since we're not concerned with the formal charges of the hydrogen atoms. So first we want to count up the valence electrons on oxygen. And so there's going to be 6 valence electrons for oxygen because oxygen is in group number 6. And then 1 for each of the 3 hydrogens for a total of 3 plus 6, which is 9 in total. But because hydronium has a positive charge, we have to take away 1 electron from the molecule. So 9 minus 1 equals 8 valence electrons. So we have 8 valence electrons that we need to account for at the end. Okay, so now we want to, so since there's only one multiple bond forming atom, oxygen, we'll just draw our oxygen atom right here. And then here's the Lewis dot structure for oxygen. Since we have one more hydrogen, we need to connect. Actually, let's connect our hydrogens next. So we want to connect our hydrogens to the free electrons. So the electrons that do not form a pair. So we have 1 free electron right here. So let's connect our hydrogen to here. And we have 1 free electron down here. So let's connect our hydrogen down here. Since we have 1 more hydrogen to connect, right, because it's H3O plus, we need somewhere to put it. Each electron is either paired or bonded. And if you remember, our electron total has to equal 8, but we currently have 9. So if we remove one of the electrons on oxygen, we can bond our hydrogen to oxygen, and we'll have a total of 8 electrons. So let's go ahead and add 1 hydrogen right here. So now for our last step, we want to draw a bracket around our molecule and then add a positive sign at the top right. So this is our H3O plus, our hydronium ion. So if we take the formal charge of oxygen, we have a total number of, so if we want to take the formal charge of oxygen, we have to first take the total number of valence electrons in a free oxygen atom, which is going to be 6, minus the total number of non-bonding electrons, which is 2, because only 2 of these electrons are non-bonded, minus 1/2 of the total number of bonding electrons. Since there are 3 bonds, 3 covalent bonds in hydronium, and each bond involves 2 electrons, we have a total of 1/2 minus 6 bonding electrons. So if we do the math, we have 6 minus 2 minus 3, which is 6 minus 2 equals 4, minus 3 equals 1. So the formal charge on oxygen is going to be plus 1. So we'll just add a plus sign next to the oxygen atom. And this indicates that the oxygen has a formal charge of plus 1, and each of our hydrogen atoms have a formal charge of 0. So if we add up all the formal charges in hydronium, we have 0 plus 0 plus 0 plus 1, which is a total of plus 1, which corresponds to the overall charge of our molecule, which is plus 1. And so for our next molecule, we have dimethyl azonide. So dimethyl azonide has a chemical formula of C2H6N minus. So it's going to be a negatively charged ion, which we call an anion. So the formal charge in dimethyl azonide has to add up to -1 because the overall charge of dimethyl azonide is -1. So let's draw the Lewis structure of dimethyl azonide. First, we have to count the total number of valence electrons. Again, dimethyl azonide is negatively charged, so we have to add 1 electron to that total. So the valence electrons are going to be the 4 electrons in each of the carbons, plus the 1 electron in each of the hydrogens, plus the 5 electrons in nitrogen. So, and then we will add 1 to that total. So we have 4 plus 4, right? Our carbons, plus 1 times 6 for each of the hydrogens, which is 6, plus 5, and then we want to add 1 to the total, giving us a total of 20 valence electrons. All right. So next we want to connect the atoms that form more than one bond, right? Since carbon and nitrogen each form more than one bond, we want to connect those 3 atoms together. We want to leave the hydrogens out of this because hydrogen only forms 1 bond. So let's go ahead and connect those. We have carbon connected to nitrogen, connected to another carbon. Right? So this is going to be that structure. So we connected 2 carbon atoms to the nitrogen in a way in which each atom shares 2 electrons with another atom, right? And then we connect the hydrogens to the atoms with the most free electrons first. Since both carbons have 3 free electrons each, and nitrogen only has 1, we will connect the hydrogens to both carbons first, since they have an equal number of free electrons. So let's go ahead and add those electrons to the carbons. So this is our structure of dimethyl azonide. And for our last step, since dimethyl azonide is negatively charged, we want to add our brackets and then add a negative sign at the top right, indicating that the overall charge of the ion is negative. So now we want to pair any electrons so that each atom achieves an octet. Since the last electron on nitrogen has no further electrons to pair with, we can pair it with the extra electron gained from the negative charge on dimethyl azonide so that the nitrogen gains an octet. So let's go ahead and add that last electron down here to give nitrogen a total of 8 valence electrons around it. So now let's find the formal charge of each non-hydrogen atom. So let's go ahead and find the formal charge for each carbon. So for each carbon, since they're identical in their electron configuration, they'll have the same formal charge. So since there are 0 non-bonding electrons and 8 bonding electrons, and since the group number is 4, we will have 4 minus 0 minus 1/2 times 8, which is equal to 4 minus 0 minus 4, which is equal to 0. So the formal charge on each carbon atom is going to be 0. So for the formal charge of nitrogen, a free nitrogen atom has 5 valence electrons. So now let's do the formal charge of nitrogen. Right, this is carbon over here. And now let's do nitrogen. So nitrogen has 5 valence electrons. Since it's in group 5, it has 4 non-bonding electrons, right? 1, 2, 3, 4. And then we want to subtract 1/2 of the bonding electrons, which is 1/2 of 4. So we have 5 minus 4 minus 2, which is equal to -1. So the formal charge of nitrogen is going to be -1. Right, so now let's go ahead and add that negative sign to the top next to hydrogen, indicating that nitrogen has a formal charge of -1. So the sum of the formal charges in dimethyl is equal to its overall charge. With that being said, that's going to be it. Thank you for watching and have a great day.